Okay, so we are going to learn the concept of electric field. So what is an electric field? An electric field is a region around any charged particle where other point charges, if placed, they will experience either an attractive force or a repulsive force. And we would see in the following lecture how do they experience an attractive force or a repulsive force. So electric fields can be classified into two categories. First one is the uniform electric field, and the second one is the non-uniform electric field. So what is a uniform electric field? Uniform electric field is one in which field lines are parallel and equidistant apart as shown. So you could see that these lines are parallel and they are equidistant apart as shown. And the reason why many people would say, right, why this specific line is curved, even though the statement says they must be parallel, the reason is at this plate and this plate, these both plates are charged, right? Positive, 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 negative, negative, negative. But what happens is, let's take an example of a point charge, right? So let's say if this is a positive charge, this is a negative charge. So how do we make electric field lines? The first line is a straight one, and as we go above and like away from like over here, what happens is because it becomes curved and curved, right? So take this field lines like this specific plates, charge plates, and assume that these are like this, like many and many positives and negative charge points, right? So these would be straight lines, and when we go away, so they become a curved line. So this is the significance of this curved line, and why again it is not parallel. Yeah, so moving on. So there's a specific property to the uniform electric field. So that is, no matter where the charge is placed, the charge would experience the same force. Okay, so like in this complete electric field, like if the charge is here or it's here, here or here, it would experience the same force. Okay, so moving on, we already know that direction of electric field is from the positive to the negative potential, like positive to negative, and from a higher potential towards a lower potential. And we know already because um and why from a positive to a negative, because we know that we always look at the conventional current, right? Because positive would repel the positive and negative would attract the positive charge, or from a higher potential, the higher potential would repel more than the lower positive potential. So moving on, the second type of electric field was the non-uniform electric field. So what it is non-uniform electric field is one in which the field lines are neither parallel nor equidistant apart. So the example which I gave above to represent why there were this curved lines in those electric field, uniform electric field. So I represented these charges, right? These charges. So these are specific examples of non-uniform electric field. So you could see that this line is going here, here, and here, and here. So these are not parallel, neither they're equidistant apart. And then comes this example where the negative charge would attract a positive charge. And then like these are all examples, right? And you would agree why um these are not equidistant apart, because there are many and many lines, and because of the curvature, so these are not parallel, right? And then they're also not equidistant apart, and you already know that because as we go away from the direct like the direct point, like this would be the direct point from the negative charge, right? If you go away like here, then the curvature will increase, and so the distance will not be equal. And and we also know of when two similar charges are kept together, or like are kept closer together, then there's a null point where there's no electric field. So basically they cancel out each other. This is a null point, right? Because there's no electric field. And similarly with the negative charge, it also happens the same. There is a null point, because um what is a null point? Basically there is nothing, right? Similar like in magnets, we know that they repel each other when there are similar poles. In electric field, and a null point is created. So this means that there is nothing over there, right? Okay, so for identical charges, the null point is in the center, right? So this charge was similar to this charge, so the null point was in the center. However, if there are non-identical charges, then the null point is further away from the larger charge and closer to the smaller one, as shown. So moving on, this is another diagram of electric field. So this is the similar diagram of that positive and negative um, charges, where the electric field line will go away from the positive and towards the negative charge. So when a proton is placed in the electric field, what happens is that the proton moves in the direction of the electric field. Why? Because we know that a proton is positively charged. So it would go in the direction of the electric field. This means that it would be repelled by the positive charge, and this would be the reason why it would go towards the negative charge and in the direction of the electric field. And and the direction of the movement of the proton would always be a tangent to the electric field lines. And then similarly, why the electron would move towards the positive charge or opposite to the electric field lines is because an electron is negatively charged. So it would be repelled by the negative charge and then would be attracted towards the positive charge. So it moves in the opposite direction of the electric field by making, again, a tangent to the electric field lines. So moving on, there's again, we already know that over here we learned something that was new, and the name was electric field strength, right? So we move on. So what is electric field strength? So when we place two charge plates, and when they are vertical, of course, so we already know that one would be at a higher potential and the other would be at a lower potential, and there would be some distance between them. So the difference in the potential, like the potential difference, like this difference and the difference between the voltage divided by the distance between the plates, will give us the electric field strength of the uniform electric field. This formula is only valid in case of uniform electric field. So what if there is a non-uniform electric field? So we have another formula, that is electric field strength is equals to force upon charge. So force is newtons and charge is coulomb. So this is another example of um, finding the electric field strength. So let's say we have a force of 200 newton being applied on my charge, and let's say the charge value is 10 coulomb. So my electric field strength would be 200 newtons divided by 10 coulomb, so it would be 20 newton per coulomb. Okay, so moving on, we already know that voltage is equal to work done upon charge, and we know that, like taking example of this specific scenario where the plates are vertical, and my charge would move. Let's say if this is a charge and it's moving uh, horizontally, right? And it is not moving vertically, right? Just horizontally, and there's no change in height. So we know that work done would be only converted into the kinetic energy. So we could replace work done with this kinetic energy formula, and by making velocity the subject, we derive another formula for velocity in electricity, that is velocity is equals to square root of twice of charge into the voltage applied divided by the mass of my charge. So then this specific formula was used to find out the momentum of my charge. So that was mass into velocity. Momentum is mass into velocity. Velocity was replaced by this specific formula, and the new formula of momentum becomes under root of twice of charge into voltage into the mass. And we already know by this formula that momentum depends on the voltage, the charge, and the mass. So we could easily, and we know that this formula, all of this formula is used for, like in this scenario where these are the plates and electric field lines are uniform. So we know that my voltage would remain the same, right? So when voltage remains constant, it remains the same, and because 2 is a constant and not a specific value of or a quantity, so in reality, the momentum of the charge depends on the charge into the mass of the charge, square root. So the next subtopic is uniform electric field graphs. Uh, yeah, so the velocity time graph is a straight line that passes through the origin. Why? Because see, what does my velocity time graph gradient shows? It shows my acceleration. So since my electric field strength is uniform, this means that for a constant charge, my force is also constant. And when my force is constant, then my acceleration should be constant. And as a result, I would have a straight line in my velocity time graph, which represents acceleration as constant. Then velocity against displacement. Since and this is the final velocity. So final velocity squared is equals to initial velocity squared plus 2 into acceleration into the displacement, or that is basically what is displacement in this case? The distance between the two plates, right? So since my initial velocity is always zero because the charges are assumed to be at rest initially, so my final velocity is equal to twice of acceleration into the displacement. And since my acceleration would be constant, why? Because we already proved over here that acceleration is constant because force is constant, and why is force constant? Because for a constant charge, my electric field strength would remain the same or would remain constant. As a result, for 2 into A is constant, then I could apply the proportionality, that is V squared is directly proportional to my displacement. And lastly, the graph of kinetic energy with displacement. Since we already discussed in the previous part that kinetic energy is equal to the work done, and work done equals to force into displacement. So kinetic energy could be related to the force into displacement formula. And since force is constant, because again electric field strength is uniform, so we could easily apply the proportionality, that is kinetic energy is directly proportional to my distance or displacement.